in general, you'll have to know which numerical one to do. You'll have to probably do a little bit of actual math to simplify that. I mean, I don't know, there's ways to do that, yeah. Yeah, you mean like the analytical one. It's not that hard. It's just a lot of chain rule. Yeah, it's just chain rule over and over and over again. In fact, we'll talk about that a bit today. Okay, yeah, we're going to there's lots of derivatives. We have to walk down things. So we have to take derivatives. Good. Other questions? Then we'll get going. Okay, hey, basic optimization. So loss functions give us loss surfaces. So here's a very simple loss surface. Think of this as being like the loss surface of a very simple model with two parameters. So two-dimensional, and the loss is in your third dimension. This is a convex loss surface. This would be a very simple optimization problem. This is actually just some kind of quadratic, so you could actually do it analytically, but you could find that you could optimize this in the sense of finding local, or in this case global optima. That's nice. This is what you learned, like maybe when you were starting to do calculus or some engineering or whatever. But it turns out that the losses that we'll work on are far worse than that. They'll have lots and lots of local minima, and worse than that. This is just like some way of kind of illustrating this in two dimensions. Our functions that we're trying to optimize will have tens or hundreds of millions, even billions of parameters. So this loss surface doesn't exist, in two dimensions. It exists in 100 million dimensions or whatever. So this in general is bad. This is bad for optimization. We would expect to end up in a local. So without getting too much into optimization just yet, doing an optimization means usually that we start somewhere and we use the curvature of the loss surface to kind of tell us where we ought to go to get to lower loss. Remember what we're trying to do. We've set like everything up this last time, so that like minimum loss is usually at 0, and we're trying to and 0 loss means we're doing well on our task. So we're trying to pick parameters that get us to lower and lower loss, ideally to 0. Although we have to take that with a pinch of salt, because at 0 you might be overfit. We talked a little bit about regularization and how you might want to prevent that. But anyways, the problem ought to seem kind of hopeless. And in fact, when neural networks were being designed, this was a massive concern, and it still, like in some sense, should be a concern. But turns out that actually in deep learning, the models that we use, we tend to find really good local minima. There tend to be lots of them, and they all tend to be, the ones that we find tend to be pretty good. And we'll get more and more into this as we learn more about what all this means. But if you're just starting off here, you might think, well, how do I do optimization? Well, I'm just trying to find parameters. So maybe I'll just start to randomly search the space. If I'm in 2D, maybe this isn't such a bad idea. I don't know. I could start to randomly sample, pairs of weights, try them out, and see what happens. This is some pseudocode around this idea. For the CFAR 10 set, you can see there's a term here that's got the dimensions. This is randomly sampling from a normal distribution, a 10 by 3073 matrix. Notice that it's 3073 and not 3072, because that additional column there will be our constant parameter, our offset. And you can pick that, you can compute the loss, and then we just kind of keep track of the losses as we search, right? And if for some reason we find something that's better than the last one, we keep track of that. Our best loss, the best W, and we just do it for, just go through it a bunch of times and see how we do. Does this seem like a good approach? Like, could this work? No. It could work. What prevents it from actually being a practical solution?
It's not very repeatable.
Okay, not repeatable. Yeah, like there's something kind of weird about just like randomly sampling the space, but random samplers, random number generators are just deterministic functions. You can seed them. You could actually repeat the search.
I don't have until the heat doesn't.
Right. So maybe in one or two parameters you might get to a solution in a reasonable amount of time. But remember we talked briefly about the curse of dimensionality. As you continue to add more dimensions here, like the size of the space is growing, by an additional dimension. Like this is becoming, so to speak, like an exponentially bigger problem as you add dimensions. And to find a global minimum would be really difficult in this way, and to find even a good local minimum would be really slow, if not completely impractical, just by searching the space like this. So if you were to go do this on the CFAR 10 and with a linear classifier, and go through 1,000 iterations or whatever, then you might find parameters that give you something like 15.5% accuracy on the classification. So as evaluated on our test set for CFAR 10. That's like a lot better than just single random. Like if you were just random. What accuracy would you expect? Well, it's 1 over the number of classes, and at 10 classes, this is already better than that. But state of the art is way better than that. So this is probably not going to work. So a much better idea here is to use information that we can get from the loss surface to move ourselves in educated directions in order to accomplish our goal, which is to reduce the loss, right? So look at that beautiful picture. There's all kinds of maxima and minima, and we're just trying to find our way down this beautiful slope to the bottom of the valley. Now, this again is just in 2D, even though it's it makes it look all majestic. Still a simple problem, it's only 2D, not 20 million D. But what's the idea? So the idea is we want to start wherever we are. Like we can randomly sample some starting values for our parameters, and then we want to just kind of look around ourselves and say which direction should I go to reduce the loss the most. And that's the idea of a derivative, right? So the derivative is in here's a formula for it in one dimension. I'm sure you remember this. Some of you with love, some of you with hate, I don't know. But nevertheless, the definition for your one-dimensional derivative. And in one dimension, what does it point to? What is it telling you? What's the derivative telling you?
The change.
Okay, it's telling you something about the change. It's the rate of change. But interpret that geometrically.
The slope.
Okay, slope of what? Slope of a line. Good. What line?
The line between the 2 points.
There's 2 points before you take the limit, but in the limit there's only 1 point, right? Because that h is going to 0. So what's it telling you?
Positive or negative.
Say it again.
Positive or negative.
The slope's either positive or negative. Yeah. What line is it though?
The tangent line.
The tangent line, right? The line that whose slope the slope of whatever the curved function is you're looking at that point. It is tangent. And for well-behaved functions, what that means is that any other line would kind of locally go through the function twice, whereas here that it would only go through your function once. Anyways, it's a tangent line. It's the tangent line, and then it's telling you the slope. Okay, so the slope is telling you what? If you move in a direction away from that point, what should you expect to have happen?
It's telling you how fast the function is either decreasing or increasing.
Yeah. So a way to think about that kind of geometrically is if I make a little change from where I'm at right now, it's basically telling me like how much the function is going to change, when I make that little change. And when I say little, it's because remember derivatives, the line you get from taking the derivative is your best linear approximation to the function, at least locally. So that tangent line in 1 dimensions is that best that best linear approximation. So it remains an approximation if I just stay really close to the point at which I'm that I'm at, where I've calculated that tangent line. So, and in particular, the slope, the sign of the slope, has to do with if I take a step in the positive direction. So if I take a step in the positive direction, then I'll expect to see that much change. So if the slope is positive, I'll expect my function to increase, and if my slope is negative, I expect my function to decrease. Okay, so this is the idea. Now, when we get to multiple dimensions, it's the same idea, except that now what we have is we have a vector, which is the partial derivatives in each of our coordinate dimensions. And what is it telling us? What's it pointing towards? What is that vector pointing towards? It's just, remember, like we could be in n dimensions, but this vector is spanning a one-dimensional space. It's pointing in one direction only.
There's 3 dimensions.
Okay, so if it's in 3 dimensions, when you say uphill, what do you mean?
Pointing like in the direction of increasing slope
Good.
of the surface.
Yeah, okay, good. So another way to say that is that the gradient, if you were to like to take that and translate it, to the point on your surface at which you were calculating this gradient, it's pointing in the direction of greatest increase of your function. So remember, there's in 2 dimensions, there's you have 2 degrees of freedom in which you could have gone. So in 1 dimension there was only really 1. I mean, there's 1 sign direction in which you could have gone. In 2 there's 2, and so forth, right? So in n dimensions this is pointing in the direction of greatest increase of your function. Now, what we're trying to do is we're trying to reduce the loss function. So the gradient is fantastic, except that it's pointing in the wrong direction. It's pointing in the direction of greatest increase. So the good news is that the negative of the gradient is pointing in the direction of greatest decrease. Remember, this is our best linear approximation. You can think of this as like, this is like defining a kind of hyperplane that's sitting tangent to our whatever the dimensional space is, and if this direction is greatest increase on this plane, the very opposite direction is the greatest decrease. So the good news is that we are on this kind of crazy loss surface. It could be as ugly as all that crazy surface that I showed in the first slides. We're somewhere in that space. We randomly chose some sort of spot in that space. The good news is that we can just compute gradients, and we know at least in which direction, if we move in that direction, we are going to reduce our loss function. That's good. That is the beginning of an algorithm for getting us to lowest loss. Okay. Any thoughts on how that algorithm ought to proceed? I'm in some crazy part of space. However many high dimensions. I have a gradient. I have a direction in which I had to go. What should I do next?
Do you change W in all a little bit in all the possible directions and figure out which one goes the lowest?
No, this is the good news, right? The gradient eliminates having to do all that searching around locally. I know that if I go in the direction of the negative of the gradient, at least locally, that is going to be the greatest decrease of my loss function. That's the direction of greatest decrease.
But also you have to calculate the gradient analytically first, and then see where.
Yeah. It's giving you a direction. So you're gonna, if you have an analytical expression for the gradient, you can just plug in your point that you're at right now, and it'll give you a gradient. You take the negative of it. That's pointing in the direction of greatest decrease, at least locally. And I keep saying locally because this function doesn't have to be linear, right? So as soon as I move away from that point, that gradient is possibly becoming a very, very poor approximation of the direction I have to go to decrease the loss. But at least right there at that point, that was the best one, right? So what's the algorithm ought to look like if I want to actually move down the surface?
Take a small step in that direction.
You gonna say the same thing?
I was going to say, move a little bit and then do it again.
Yeah, good. You're both saying the same thing. Use that direction to move a little bit. Now you're in a new part of space, on the loss surface. Very likely, you're at a much lower loss because you took a small step and you used the gradient, the negative of the gradient, to tell you which direction to go. And then you just do it again. And you do it again, and do it again, and do it again until the loss stops decreasing. And at that point, you've converged. Well, this algorithm can be said to converge. That's pretty good. That's actually, that's the basics of a very well-known algorithm called gradient descent, which you might have heard of before. So it kind of looks like the following. If we've got weights, however many weights we might have, here's just some, what do we have, 10 there? And the loss is, at some value, whatever it is. What I want to do is, I want to, I forgot that I do it this way in these slides. One second. Let's get through this. Yeah. I forgot that I have these slides that kind of motivate all the things I just said right there. What these slides right here are telling you is that one way you could do it is kind of like what, I forgot your name, but was suggesting is that you could start to you could pick a direction in which you could go, and you could calculate. That's a new set of weights. You could calculate an approximation to the gradient by taking the difference of these two things and moving in that direction. And hopefully, your loss will decrease in that way. But this is silly. Remember that our losses are just functions of our parameters, so we can just compute gradients with respect to our parameters. So this symbol right here is what we're going to, be thinking about a lot. That's what we were just talking about. The gradient, the negative of the gradient is the direction we want to go into. Yep. Newton, Leibniz are best buddies from centuries ago. Gave us the tools we needed a long time ago. If we can compute this gradient, then we know which direction we ought to point into to move in, and we ought to just take some little steps. And in your homework, if you've already started it, you probably have seen this. You're going to be implementing gradient descent for doing all of these some of these problems where you're optimizing picking parameters, and you're going to need to be able to calculate gradient analytical gradients. That was the question that was asked earlier, so that you can quickly move in the right or you can quickly compute these gradients, but you can also check whether or not that gradient is correct or not by just doing this very simple, change in a small change to your parameters, calculating the difference between all your parameters, dividing by that change, and having a numerical approximation to that. And you'll see in the homework that there's a bunch of this. There's like we will check your analytical expressions with these numerical ones, and it's not a bad way to check yourself as you're doing this. Now the truth is that tools like PyTorch do all this for you. You never have to actually probably compute a gradient ever again in your lifetime. Just like when you got MATLAB or whatever it was that you're doing, you never had to compute inverse of a matrix again by hand. But anyways, we're being forced into kind of learning the basics here so that we can appreciate PyTorch and TensorFlow and JAX and all the other libraries that are there. So gradient descent, as we already discussed, is this idea of computing gradients and then updating our weights by taking a small step in the direction of the negative gradient and then updating our weights or changing them accordingly. So if you know Python, this is an in-place operation to add this to weights. And so what is this doing? This is subtracting off a step in the direction of the negative grade. Well, subtracting it in the direction of the grade. So it's adding to it a small scale step in the direction of the negative grade. So it's pretty simple to write down, and this could work, especially with enough compute available to you. But there are some problems with it. Before we get to problems, what does this look like? So this is a heat map of some kind of very simple surface, where the redder it gets, the lower the value of our loss function. If we're here and we compute our gradient, we ought to be pointing in the direction of greatest increase, which would be something like this. So the negative gradient gives us the direction of most decrease. Sorry, I said that wrong. The greatest increase, this would be the greatest decrease. And then we'd be taking some step there. That gives us a new set of weights, and we would just do this, and we'd hope that we would get to the minimum of this surface fairly quickly. Okay, so that's great. Let's think about this practically, though. What are some of the issues involved? Just what are some problems that could happen that you can anticipate with gradient descent?
Probably the local minimum, but not a global minimum.
Okay, so we could move to this algorithm, because we're starting at like a random part of space. It's going to move us towards whatever's like kind of the nearest local minimum. I mean, like nearest is not exactly right. This all depends on like like the step size and things like that. But yeah, there's no guarantee that we're going to converge to a global minimum. We will converge to a local minimum eventually, or we will get close to one anyways. But yeah, so there's that. We're not going to be able to overcome that with gradient descent, but we're going to still use gradient descent. So what are some other kind of problems you anticipate with gradient descent? Okay. Yeah, so there's this whole thing about step size. Like how do I choose the right step size? That's going to be a problem that's going to exist, and we're going to have to think about and deal with. And there's like a whole bunch of kind of like heuristics for dealing with that. In general, can you think of a way to deal with, like, to choose step size, again, using local information? or anybody? Yeah.
Maybe if you have a bigger gradient, you'll choose a bigger step size. If your gradient is smaller, it would be smaller step size.
So what does large or small
Like
gradient mean here?
Proportional to the, like not the negative, not the sign of it, but
Like the length of the vector?
Yeah.
Okay. Yeah. So a longer vector is saying something about like how much it's increasing there. But maybe that's okay. Maybe that's right. Maybe like, you know, maybe it really does increase all that much there. But you're thinking right. Let's see, who was having that next?
You should first continuously change the step size. At first, the step size should be bigger, and as we continue, it should become smaller because we are going to near the local minimum.
Okay. So here's like a heuristic that might be useful, is start with large step sizes and then reduce those step sizes to be smaller because we expect to be getting closer to some kind of minimum. How would we know like the rate at which to change that? Kind of a tricky problem, but yeah, I think that's a great idea.
Yeah, the same idea. So the step size can be a function of time or the number of iterations.
Uh-huh.
And there are several heuristics that using the inverse of square root of time or something.
Okay.
Like that.
Okay. Yeah. So like, there's a good idea emerging here, which is, as we go along, we probably want to reduce our step sizes because we think we're going to be getting closer to a minimum, and we don't want to like overshoot it. So you see, the problem with having a large step size is you might be really close to a minimum already, right? Like whatever iteration you're at. If it's a large step size, you'll step right through that, maybe into a whole different part of your loss surface that has like now another local minimum that, you know, is somewhere else, and you know, and you're not going to get back to this other one. You stepped way over it. So yeah, like you want to be able to control that in some way. I thought there was another hand over here. Okay. Yeah.
So do we use the gradient of the gradient because that will tell you how much the gradient is changing? Right?
Okay.
So if we
Yeah.
not changing as much.
Like the gradient of the gradient. So there's an object known as a Hessian, and these are all the so it's a matrix. It's all the second partial derivatives, you know, with all your variables, and it tells you something about the curvature of the surface where you are locally. So this is actually pretty useful because it will tell you, like, basically if you have the Hessian, you can construct the best quadratic approximation to your function. So it's no longer just a linear approximation, but a quadratic one that's taking into account some curvature. So that should allow you to pick a better step size because you have a better approximation locally. However, you can see how that might break down if you have like, you know, higher order behavior as well. But it's a really good idea. Like you're using this kind of information to like, you know, pick a step size. And actually, there's a lot of what are known as second order optimization schemes that use the Hessian. In general, though, they're not used in deep learning because we're doing lots of iterations of gradient descent, and calculating a Hessian is like an n squared operation, and you know this becomes prohibitive if we have lots of weights. It slows us way down, and so we tend to actually just use first order optimizations that just use linear approximations, just use the gradient. But it's a great thought. It's a great idea. Good. In general, there's going to be no real rule here about how to pick the step size. Like something that we can both prove you know, works, and we can practically use, because we have this trade-off between higher order approximations and the cost of generating those. So this is going to be a problem, but there are heuristics that kind of look like some of the things that you all mentioned that we typically follow when training neural networks. These are sometimes called learning rate schedules. Well, I guess they're always called learning rate schedules. And there are some very common ones that are, you know, that are thought to work fairly well. And we'll learn something about that. All right. So there's another big problem that hasn't been mentioned yet with calculating gradients of losses. And it's actually on the board here.
It takes up lots of time.
Why does it take a lot of time?
Gradient.
Gradients take a lot of time to calculate, yeah. Although, I guess it just depends on what you're taking the gradient of. Like, one of the cool things about neural networks is that we actually have a bunch of simple functions all chained together. So we have linear functions, and then there's like nonlinearities that kind of join them together. But they're very simple. They're often just like entry-wise. So actually, the derivatives of at each of these steps is very easy to like analytically write down. And then thank goodness we just have a chain rule that that just like gives us the products of all these things along the way. And so actually, like, this ends up being quite fast. I mean, it is prohibitive at some level. I mean, and it is like a lot of the computational cost comes there. It's actually not that big of a deal to calculate, say, like the derivatives of our individual loss functions. The other huge problem here is the way that we've defined our loss functions. Remember, in general, our loss functions are the average loss over all the data points in the training set. So if we've got millions, tens of millions, I mean, people are training on, hundreds of billions of data points. We can't at every iteration recalculate the loss and and then all those gradients for all those data points. That is actually extremely prohibitive. That we cannot do. We need a lot of data. You probably you've heard this a bunch of times. Deep learning needs a lot of data to work, but the loss functions we're trying to optimize, are based on being able to compute the loss for every single data point. That's a problem. So how do we get around this? Batches, yeah. The answer is right here on the board. So we do something what has become termed stochastic gradient descent. So given a data set, this is our loss. Yeah, very expensive. So what we want to do is approximate that loss. We want to approximate it by something. We want to estimate it by something. What do we want to estimate it by? Well, maybe the simplest thing to think of is say, let's just randomly sample some data from our training data set and just compute the loss with that small sample. And this is what is known as stochastic gradient descent, or we often just abbreviate it SGD. And the idea here is that every time we want to update our parameters, we don't calculate the whole loss. We sample what's known as a mini batch, or just sometimes just called batch, if we're sick of saying mini, a randomly sample from our training data, and then compute the loss just with that mini batch. And I'll tell you right now that this is like this stochastic gradient descent and like a whole bunch of variants of it, all of which are using this kind of mini batch sampling as you iterate, is the standard in deep learning right now. Do you see problems with it? What?
It doesn't come, when you sample, you might sample just a specific subset.
So like, yeah, specific subset, and maybe the idea you have there is that subset could not be representative of the whole training set, right? It could be very biased, in which case our estimate of the actual loss, or like the gradient, our estimate of the gradient of the loss, would be a really poor estimate of the actual gradient of the loss if you were to compute it over the whole training set. Yeah, that could happen, absolutely. And I mean, in fact, it's an estimate, so it's not likely to be pointing in the direction of greatest descent. So, yeah, that's a problem. And yet, this actually is how we're going to optimize our neural networks, our huge neural networks. We're going to do this. We're going to use these very noisy estimates. In fact, our training sets are going to have you know, a whole bunch of, you know, million, tens of million. Like I was saying, there's data sets now that people are training on that are enormous, in the hundreds of billions of samples. But our mini batches will often be tiny compared to that. I mean, vanishingly small, right? Like this all kind of depends on like what GPUs you're using, or how many of those you have, and how much memory each of those, you know, has, how large the model is that you're storing as well in those GPUs. And so it's not, especially for like a data set like CFAR10, it is very common to have very small batch sizes, 32, 64, 128, always powers of 2. If you do something that's not a power of 2, you better be ready to like justify that, because like you don't get asked questions if it's a power of 2. People are just like, yeah, you know what you're doing. But if it's not that, then you have to answer. You know? And usually, what you're really trying to do is in practice, you're really trying to just fill up the memory of your GPUs. You know, like your model's going to take so much space in your GPUs. And then you're going to have so much space left over, and you just want to like pick batch sizes so that you fill that up. Now, there are other things you have to pay attention to that have to do with the architecture of the particular GPUs you're working with, or other accelerator hardware like TPUs or something like that. And each one has some magical numbers that if your mini batches, you know, are of the right size, the computation will be faster. But in general, this is kind of how we proceed. Anybody? Okay, so I told you all that. Yeah, question.
Quick question. So when selecting the batch, did we ever stratify the samples or the batch based on that?
Stratify how?
Stratify based off of like the output variable? Or
So yeah, so like for example, if we're doing a binary classification problem and our data set happens to be 50% positive, 50% negative, you know, then we'd want our batches to also be 50% positive, 50% negative. Is that what you're getting at?
Yeah.
Yeah, you can definitely do that. Stratified sampling is definitely a thing. Turns out that like sampling is also one of these heuristics where you do want there to be random sampling, but truly random sampling is very expensive as well, in terms of like, you know, actually, you know, determining what those will be via, you know, random number generation, and then going to read those off of wherever they're stored, because that would be like a random access read. That actually can be quite slow, and so you really want to speed that up, especially for very large data sets. And so there's ways of like getting kind of pseudo-random behavior by like maybe upfront randomizing everything, like all your data, and then just kind of going through it chunk by chunk, like you know, whatever your batch size is. And so you're not, you know, this looks like sampling with replacement. What I just described would be sampling without replacement, running through the whole data set. That's typically referred to as one epoch. Maybe you've heard that before in deep learning, but now, if you haven't, now you've heard it. One epoch is running through all of your training data, and then starting over, maybe randomizing again, or you know, working through it, reading through it in a different, you know, like not quite random, but like pseudo-random way, just so you can speed things up. It really has become like deep learning works because we have fast accelerators, so our GPUs and TPUs, and we want fast. We make a bunch of approximations to speed up what should be like the actual algorithms by doing stochastic gradient descent and by doing some of these kind of heuristics for getting pseudo-random sampling of our data. Okay. Yeah, there was something I was going to ask before that, but I forgot what it was now. But anyways, any other questions about this? I think what I was going to ask was like, is anybody still feeling worried about the fact that we're going to approximate a gradient that's computed using maybe 1 million data points with just 32 data points? Anybody feeling worried about that? I mean, I think that's natural. It turns out that it works. I'll get to you in just 1 second. It turns out that it works, and actually, it turns out that this, I mean, not for all choices of like the hyperparameters of the mini batch size and like learning rate and things like that, but it turns out that actually this randomness that you build into the the estimation of your gradient actually is thought in general to act as another type of regularization. So it prevents overfitting because you're not actually walking down the exact gradient, and you tend to find better local minima according to certain ways of thinking about what does it mean to be a better local minima if you do this. And it's been verified empirically over and over again, and there's some theory behind it as well that makes a bunch of approximations along the way as well. So whether or not that's it's very much in the spirit of like empirical physics. Anybody here like a physics PhD or majoring like that? Just want somebody? No, nobody is. Okay, so I guess we can bag on them then. No, actually, their way of doing empirical science is definitely very much in the spirit of how we're doing it here. So it works. Okay, there was a question back here.
Yeah, this is kind of going back a little bit, but if we have to take an analytical derivative to find the gradient, how do we do that when the function we're taking derivative of is just a function of weights, but the input image affects a loss. If you give it an image, it returns a loss.
Yeah.
How do you calculate it?
Yeah. So I think what you're saying is the loss is not just determined by the weights, but also the data set. That's right. That's exactly right. So the data set is as a part of the definition of the loss. You can think of it as fixed, like for the perfect loss function where we calculate over the whole training set. So those parameters aren't changing, but then it's actually not fixed, right? We're doing this mini batch sampling. So just think of it as just think of the data that you choose here as a way of creating a gradient that's an estimate of the true gradient. And then we don't care, we don't typically care about how the loss function changes with respect to the data. We think of the data as fixed even though we're changing it over and over and over again. So we're not taking derivatives with respect to it. Now that's not 100% true. Later in this course we'll look at ways of understanding how a convolutional network is working by actually looking at gradients with respect to the individual pixels themselves. But that'll be just a way of thinking about how the data is influencing the loss function at a particular set of weights. And when we get there, we'll address it. But in general, to do this optimization problem for reducing the loss, we think of the data as a fixed parameter. We're not optimizing with respect to it. It's true that everything will change, so to speak, if you change the data set. But that is as it should be, right? We expect there to be different parameters. Oh no, we're doing this again. I wish there was a simple way to fix that. Maybe there is. Is that what I said last time? Oh yeah. You guys are awesome. Thanks for being the memory here. Let's see, what was I saying? Oh yeah, just think of that as being fixed. And oh yeah, what I was saying is for a different data set, you'd expect there to be different parameters that would be best for that data set.
So do we not need to know the details of calculating the analytical derivative?
No, you do. It is, but you're just not going to be calculating with respect to the data. You'll be calculating with respect to the parameters. But you'll see in all these kind of simple formulations that the data just kind of goes along and it enters simply into the calculation, right? Like for a linear function, we just have a linear, we have a product of weights times data. So if I'm taking derivatives with respect to the parameters, the weights, then I'm just left with data.
So essentially the math is 3D but it's
Yeah, but in general, just think of it as some other parameter, and we'll be calculating these things, and there's going to be expression for the data or components of the data in that analytical derivative, and you'll be able to deal with it, I promise. Okay, so there's kind of something fun here.
Sorry.
Oh yeah, sorry.
I was just going to say also that I kind of ran into problems, like when I was working on the homework, I ran into problems like knowing how to actually calculate the analytic gradient. That actually website right there, that like Stanford.edu/whatever/CS23.231N, like that has kind of material like related to this, and that helped me figure it out.
Yeah, that's great. In fact, if you look at this, if you look at the syllabus, there's additional links to like remembering how to do analytical derivatives and things like that. And yeah, some similar material is here as well. Maybe we come back to this if we have time. We're kind of running out of time, but also these slides are just up. You know, they're up on Canvas. This is something you can go kind of play with, and you know, watch a linear classifier for 3 classes update itself via gradient descent. You can change things like the step size and you know where you start from and things like that. Okay, so in the time remaining, what we want to talk about is computational graphs. So now we're going to move from you know this kind of basic understanding of what we're trying to do. We're going to be doing gradient descent, stochastic gradient descent to optimize our models. And the models are what we're going to think of as our computational graphs. They're going to be flows from input, compute, to output. And the reason why we're going to like think about it like this is that this will make it very easy to then think about where all the derivatives are eventually in these very complex neural networks, and to think about algorithmically computing those gradients over very complex models, which translate to complex computational graphs. So I heard some excitement around when I said computational graphs. Maybe some of you are doing this in your classes already. This is a very common way to think about what we're doing with neural networks, and to think about just to think about the problem, just think about the different problems there are when trying to speed these kinds of things up. So the idea of a computational graph is just to represent your inputs and your operations and as different stages where you're composing the output you're composing your operations so that the output of one operation becomes the input of the next operation. That's the composition, and so on and so forth. And the arrows are taking us, from one operation to the next. So very simply, something that we've already looked at, if we want to compute the hinge loss for a particular data point in our data set, here is this analytical expression for it, and these scores are given to us by this linear function w times x. So what does this look like? Well, the inputs to be able to, at a kind of a high level here, the inputs to this look like the data and the weights of our function, the parameters of our function. And in this case, what does the function do? Well, in general, it can do a lot of complicated things, but this thing just does a matrix vector product. That will give us the scores across all of our classes. Those then get entered into hinge loss, and this itself could be broken up into other operations, but just kind of at a high level, we think of that this is taking the scores and doing this operation. And then we might actually add to that some regularization term. So there's another operation. This regularization term is just a function of the weights. Add those together, and that becomes our loss function. So this is a high level kind of simplified way, a simple computational graph for this loss. If we want to now compute the gradient of this loss, perhaps this seems more reasonable, because what we're doing by thinking of these operations as like, being composed as we walk along the arrows, then we remember our calculus, remember that composition when taking gradients is handled by the chain rule, and that we get these products of the gradients of the different operations along the way. And so now maybe this seems a little bit more reasonable, at least like maybe we're organizing what we have to take derivatives of, and we can think about this in a more rational way. Algorithmically, this is definitely how we're going to implement these kinds of things, because we're just going to have, basically, ways of specifying what's data, what are the operations, and then what are the derivatives there, and then put these all together via however the composition happens. So that's a simple computational graph. This is a more complicated one, where we have a deep neural network, where at each stage here we have a convolutional layer which has its own operations and its own way of computing gradients, and that's of course something we're going to do here in just a couple of weeks. And it's going to be even crazier. Here's some kind of computational graph for something that was popular a few years ago, a neural Turing machine, and the reason I show that here is because this thing has multiple steps in it, where at each step we actually have this whole computational graph repeated. So this maybe seems less organized than you might hope, but actually if you just have, if everything's just connected, like if you have identities for things at your nodes, and you have ways of connecting those nodes up, this just becomes, even in this really complex situation, a very rational way to think about where are all my gradients, what's the input, what's the output, and then how do I put this all together to getting one final gradient that I will use to do my stochastic gradient descent step. At the heart of this is the chain rule. So if we're composing functions, so f compose g, this means that whatever our input is, we first apply g to it, and then we apply f to the output of g of x. If we have a composition like this, and we want to take derivatives of the outermost function here with respect to the input, then I just have the derivative of the individual functions in this, and the products. I have the products of those individual derivatives or those gradients. And sometimes people get tripped up here when they see that this is with respect to g, but remember this is just with respect to the input of this function. So I mean, this is in some sense just a dummy variable, and it's g there because that is the input to f right now, whatever the output of g is. But they're just kind of dummy variables to say, in this one-dimensional case, that's what this looks like. And yeah, if you want to think about this again, like in the ways that we were discussing it earlier, the way that the whole, like the final output changes with respect to the input is that each one of these is giving us the rate of change for the individual component in the composition. And the chain rule just says, actually we're just multiplying those all together. So we get a certain rate of change from like the inner function, then we get another rate of change from the outer function, we multiply those together, and that's giving us the overall rate of change there. So just hopefully for all of you, just a quick reminder of what, of your multivariable calculus courses. This is a really silly, diagram for this, but sometimes people really like to see silly diagrams because they help solidify, complicated concepts. So the important thing that for showing this is that each of these functions is just an operation taking you from input to output, and you're chaining all these together. And thank goodness that this is how, like, there's a really simple rule for computing the derivatives of, you know, what can look like very complex compositions of operations. Yeah, that's like just an awesome graphic. All right. So more generally, what does this look like? Well, fortunately, it's still the same thing. So that was all kind of, you know, it applied if it was still, you know, multidimensional, but you know, you probably learned that, you know, and remember this for like single-dimensional problems or inputs. But in general, you know, we could have a multidimensional input, you know, of dimension m, and then that could be operated on and take us to something of an output of dimension n, and then that output of dimension n would take us to a single-dimensional output. That would be like our loss, right? Our losses, we define losses so that they give us a single number to tell us how well we're doing on the task. So what does the chain rule look like here? We're just going to name some dummy variables here to keep track of things along the way. X is dimension m, y is dimension n. That's what that mathematical notation means there. Again, y is dimension n, and z will be a dimension 1. It's a scalar. That's what, again, that notation means there. How do we think about the chain rule in this case? Well, if we think about all the partials with respect to each of the entries in our m-dimensional input x, if I want to compute the partial derivative of the final output with respect to that, the ith input, or the ith entry in the input, then I just have to do this chain rule, but consider all the paths through the adjoining variables here. So for each of the for each of the m entries in x, I want to consider each of the n entries in the output y. I want to look at the final output there, z, take its derivative with respect to that, and then thank goodness it turned out this way. We just have to sum all those up. So now when we're thinking about like how this works in a multidimensional sense, when our output is this one-dimensional variable here, what's nice is we have the chain rule for each of those, like for each of the ways we could go from an entry in x to an entry in y, but now we just have to sum all those up. So that becomes, again, really, really quite simple. So you know, the compositions give us products of rates of change, and then we add those rates of change together as we go from entry to entry in the input. So very nice, simple mathematics here, which is making our gradient descent algorithm even simpler to think about. What's cool about this is that you can write this down in like vector or matrix notation, and so this right here, this gradient here, or this partial derivative here, is actually a matrix of values, and I guess m by n, and then we multiply that with the gradient of z with respect to its entry. So this is like another way of expressing this right here, but more what looks like a chain rule, but in higher dimensions. So the gradient of the final output z with respect to the input x, again, looks like a chain rule, a product of gradients, but we just now are kind of keeping track of all kinds of different partial derivatives through this matrix here and this in this vector here, which is cool. Like, it's just nice. Like, maybe it looks ugly, but the truth is, linear algebra is all about like keeping track of indices, and that's all this is right here. It's just an accepted way that we've all agreed upon for keeping track of indices that that basically is this computation here. Is there a question? Yeah, yeah, probably. I mean, I have to review it all the time too. It's not like born learning or knowing these kinds of things, but this is just think of this as like ways of keeping track of all the indices involved here. Cool. All right. So yeah, this could get quite complicated. In fact, here's an example of what we're eventually going to be doing, right? Like we're going to have neural networks. We're going to have at each layer in our neural network, there's going to be different numbers of inputs there. They're going to be projecting the different number of outputs that match the input to the next layer. And these are literally just compositions of these linear functions. This isn't necessarily linear here, actually. This could be these could be any functions, but the outcome would be the same in terms of what the derivatives would have to be. We have the products of each of the derivatives of each of the layers here, all put together in the right order. We're keeping track of the indices so that we get all the products right, and voila, we will have the gradient of loss. Now, like in kind of summary form, this is what it looks like. But like in practice, what do we actually do? So what do we actually do? Well, in practice, after we get through this class, after we get through like the first few weeks of this class, you'll just pick up your favorite deep learning framework, and within it, it'll have modules for doing what's called automatic differentiation, which is essentially taking those, like basically just for every operation that's defined within the framework, there will also be an analytical derivative associated with it, and it will know about that, and it will it'll know everything about the chain rule, and it will just do all this for you. You will not compute your own gradients. You will just put differentiable functions or almost differentiable functions into you'll define these things, and you'll be able to put them into your code, and the code will be able to look at those things and will be able to say, this is actually the computational graph. It'll expand that whole thing that you've defined in kind of a high level declarative way, and then it'll say, oh, okay, cool, I can expand this to what the actual computational graph is, and then it will say, I know how to do differentiation along this whole thing because I can do it automatically because I have all the rules defined in me, and it will just happen. So you'll love that because you'll hate doing this by hand the one time that you have to do it in this class. Although you'll probably appreciate knowing something about what's going on, and this will also allow you to debug things when things aren't going right. Anyways, yeah. So I'll skip. So yeah, the basic idea here, like I just said, is that for every function that's defined in your, you can think of them as transformations. Every transformation that's defined within your framework, there will already be a kind of like analytical expression for that function, and that's what will be used in automatic differentiation. Okay, now the algorithm. How does this actually all happen? Well, there's an old algorithm known as backpropagation. That is the key algorithm for computing gradients in neural networks and in like gradient descent problems, in general. And I'm gonna introduce you to this right now, and we'll spend more time on it the next time that we meet. This is really critical. So a lot of things have come together to make deep learning work the way it works, and one of the really important elements of that is this algorithm of backpropagation. So what is it? Well, basically, it's just a way of like taking your computational graphs and keeping track of things as you work from the output back to the input in terms of computing gradients. So here's a function, a very simple function of three variables, x, y, and z. Let's assume that right now we are, we're at the point x equals -2, y equals 5, and z equals -4. Okay, so what does the computational graph look like for this simple operation? Well, we have three variables. We will, order of operation here matters. Well, maybe not for this, but in general it matters. And what do? Well, we first add x and y. So we have our variables x and y are inputs. We have an operation plus. And to that we multiply z. So we have our plus x and y. Whatever the output of that is, we multiply to that z, and that gives us the output of our function f. Right? Again, very simple computational graph. We have two operations here, this sum of x and y, and then this product of the output of that, which we'll call q as we're kind of tracking things here. The q is equal to x plus y. And then the product of that, q, with z. Okay, so what are all the partial derivatives at each point here, or at each part of the operation? Well, let's start with our sum. This is pretty easy. If you remember, how to take simple derivatives and how to do this in multiple dimensions to do the partial derivatives. So first, I have two inputs, x and y. I want to calculate each of those partial derivatives. So first, I calculate the output of this, I calculate this function x plus y, the partial derivative with respect to x. So I look at this and I see I've got an x right here. For right now, I'll just run this for a second. The partial derivative of x with respect to x is simple. That's just 1, right? And now I look over here and I have another variable y, but x and y are both like independent variables inputs to this function. So y is like a constant with respect to x. So when I take the partial derivative of y with respect to x, I get 0. So the partial derivative of x plus y with respect to x is 1. Meaning, as I change, as I increase x by a little bit, q, the sum of this will increase by exactly that amount. That's what this rate of 1 means. And then similarly, when I do the partial derivative of q with respect to y, just similar arguments apply, just swap the variables. So now I also get a 1. So very simple partial derivatives here. It's almost as simple, but not quite, for our other operation. So f is a function of q and z. So when I take the partial derivative of f with respect to q, because this is a product, and I remember my rules here, I'm just left with z. So again, remember, think of this as like the rate of change as I change q. So as I change q by a little bit, I add to that z. That's what this is saying here. To get f, and the same thing is happening here, just vice versa. There's symmetry in those input variables. So instead of if I take the partial derivative of f with respect to z, I get q. Okay, cool. So I have the partial derivatives at every operation here. Okay. But what I really want is I want the partial derivatives of the output of my function, the full function, with respect to the inputs x, y, and z. And I don't have those there except for right here. I've already calculated that. But the other ones we don't have. So what do? Well, you could approach this in a number of ways, but we're going to approach this in the way that the back propagation algorithm works. So what it does is it starts at the output, and it says, what's my derivative with respect to, so all along the way here, I'm going to want to compute the derivative of my output with respect to the input at that stage. Well, the input at this stage is just itself. So this algorithm kind of like initializes itself by saying, what's the rate of change of f with respect to f? This is what? Yeah, just 1. I mean, it's maybe a little bit silly, but this is how we initialize this. So we say, okay, you know, I started off with a gradient here of 1, all right? And then I start to work backwards. I'll go, okay, if I want to compute the partial derivative of f with respect to z, I look at this and I can say, well, I've already calculated that. It's q. And what is q in this particular problem? We calculated on the forward pass. It's 3. So I have the partial of f with respect to z is 3, and there's like a null operation happening here, which is like the product of this and this. The reason we're being pedantic about this will kind of show up a little bit later as we get more into this algorithm. Okay, so we want partial of f with respect to x, partial of f with respect to y. So back propagation says, okay, let's work our way back from here to here. So what is the partial of f with respect to q? Well, we've seen that it's z. And what's z in this case? Yeah, z is the is the full output of this, and it's -4. So this partial derivative at our inputs is -4. Okay, so we have a -4 there. And now we work back through. Well, we want to calculate this, right? This is one of the things we want to calculate. So to do that, we use our product rule. We've got f with respect to q, and now we need q with respect to y. And we've calculated that before. Oh yeah. So this is again the chain rule. We have our chain rule is the upstream gradient multiplied by the downstream gradient. Now, the partial of q with respect to y was 1. So when I multiply these two things together, 1 and -4, I get a -4. And similarly, because this is still -4, and the partial with respect of q with respect to x is also 1, we multiply those two things together, and we see this is -4. So we now know, at least at these values of x, y, and z, what the partial derivatives of our output are with respect to our inputs. They're -4, -4, and 3. Oh, that was the end. Yeah, good, because we're now done. So this is very, very simple, but this is the idea of backpropagation, is that we start from our output, and we're going to work back through these arrows, computing the gradients along the way, and then multiplying those along the way. And so what we're building up is like the full product of all of the intermediate steps from the input to the output that started from the back. And that's why it's called backpropagation, because it starts from the end and works backward. We're propagating gradients backward. Now, next time we'll get into something far more complicated than that, that will hopefully illustrate this, and then you'll kind of have an appreciation for what backpropagation looks like. Okay, thanks everybody.